Good day, learners. Welcome to our mathematics lesson for today. My name is Nagile Ndlovu. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Right, our focus for today, boys and girls, is going to be trigonometry. And today we're going to specifically look at the cosine, sine, and area rules. Sine, cosine, and area rules. We are saying by the end of this lesson, you should be able to prove the sine rule, prove the cosine rule, and also prove the area rule. There are three rules that we apply under trigonometry, not identities but rules. These are the rules that can help us calculate missing sides in a non-right angle triangle. These are the rules that can also help us calculate the area of a triangle where there is no 90 degrees. So you should be, by the end of this lesson, be able to apply the sine and cosine rule. After having proven those, you need to apply them. How do we apply them? We apply them by finding missing sides and angles in the given triangle. You should also be able to find the area of a triangle by using the area rule in a non-right angled triangle, which means there are those types of triangles that don't contain a 90-degree angle, of which it will be difficult for us to identify the height after having picked on a particular base. So for such triangles, we've got a special formula that we use. This formula is called the area rule. Right. These are things that I expect you to know by now. We have been looking at these things before or in the previous lessons. The definition of trigonometry, the definition of sine, cosine, and tangent in terms of their trigonometric ratios based on that Cartesian plane, and the first quadrant or any other quadrant defining the ratios. But usually when we define them, we use the first quadrant. Then types of triangles, you'll remember you did quite a lot of triangles, three-sided shapes. They come in different types. Then you have done right from lower grades, Pythagoras' theorem, then area of plane shapes. There are some selected terms that we are going to define today. For example, what is a triangle? Yes, a triangle is a polygon with 3 vertices, 3 sides, and 3 interior angles. And don't forget, those 3 interior angles always add up to 180 degrees. Then a right angle triangle, to be more specific, is a triangle which contains a 90-degree angle. Then a non-right angle triangle is a triangle which does not contain a 90-degree angle. So if any triangle is presented to you, you study the diagram, you don't make any assumption, you don't see a 90-degree angle, unless if you have got a reason why you are saying it's 90. Otherwise, that triangle is a non-right angled triangle. It basically doesn't contain a 90-degree angle. Then we have mathematical proofs. A mathematical proof is a logical way of demonstrating that a given statement is true. For example, prove that the sum of the interior angles of a triangle is 180. That's just but a statement which can be proven, then it will eventually become a theorem. Then a rule in mathematics is a set way to calculate or solve a problem. It is a set way or a prescribed way of doing something. That's what a rule is all about. So those rules that we mentioned earlier on, the sine rule, the cosine rule, and the area rule, are a set of ways of calculating missing sides in a triangle, missing angles in a triangle, or to find the area of a given triangle. Right. We are going to have a look at how these rules are proved or proven. The first rule that we are going to look at is called the sine rule. So I have listed there all the rules that you need to prove today. We are saying in any given triangle ABC, alongside the sketch, you can see the sketch there, ABC, the sine rule states that if you take the side A and divide by the sine of A, it will be the same as taking the side B divided by the corresponding angle side B. Then take side C divided by the sine of angle C. This should be angle C here. It should be angle C. So the sine rule states that A divided by sine A equals to B divided by sine B equals to C divided by sine C. The question is, how do we label a triangle? You'll realize that on the sketch given alongside, the capital letters always go to the vertices. We don't take things for granted. Sides are never labeled using capital letters. So our capital letters in any shape, when you are naming a shape using letters, we use capital letters at the vertices of that particular shape. So our triangle given is called triangle ABC. When you look across A, there is a side that is in front of A there, big A. That side BC is called small a. So our side BC is called small a, and our side AC is going to be called small b. These are small letters that are based on the letter that is directly across. Then our side AB, we are going to call it, this is side AB. The other name for side AB in this triangle will be our small c. So we use small letters to represent sides and use capital letters to represent our angles. Okay, right. So what then are we saying here? We are saying for the cosine rule states that a squared, if you are looking for this missing side a, let me remove these other sides for you so that you can easily see a, right. If you are looking for small a, which is this one, is missing in your triangle, the other two b and c are known, how do you proceed to find angle a if, side a, if angle a is given? This angle needs to be given, then these two sides also need to be known for you to find the missing side, which is a. In other words, a is unknown. This is where we are going to say a squared is equal to b squared plus c squared minus twice the product of bc multiplied by cos of angle a. We shall see where these rules come from. Then the area rule states that in any given triangle ABC, the area rule is area of triangle ABC is half AB multiplied by sine of C. In other words, you need any two sides and an included angle to calculate the area of that particular angle, triangle, without necessarily using the perpendicular height. As you can see, this triangle does not have a perpendicular height. Neither am I going to drop one and find its length. There is a sufficient formula for that, which allows us to find the area of any given triangle, whether we have a 90-degree angle or it's a non-right angled triangle. We can still find the area of that triangle. So basically, these three that you see today, which is your 1, your 2, and your 3, are the three rules under trigonometry that you need to know how they are derived, where were they taken from, and also apply them to answer the questions or to solve a particular given triangle. Right. So we'll start by having a look at how we prove the sine rule, proof of the sine rule. So we're saying in any triangle ABC, we have already indicated that A divided by sine A is the same as B divided by sine B, which is equal to C divided by sine C here. Right. So these are ratios. These are ratios. If you compare a side with this angle in sine, they will always balance the three of them. Alternatively, our sine A, we can even reverse that fraction and start with sine A over small a is the same as sine B over small b, which is equal to sine C divided by sine C. Right. So we are forming fractions either way, starting with sides at the top, then sines of angles at the bottom, or we start with sines of angles at the top divided by their corresponding sides. At the end of the day, we are saying those three are going to be equal in value. Okay. Right. Let's have a look at how we derive those. We are saying consider an acute angled triangle ABC. We are given an acute angled triangle ABC. We are going to identify some sides. The side that is opposite B is small b. The side that is opposite angle A, when I say angle A, focus on capital letters. Angle A is small a, which I have highlighted there using that long arrow, red arrow, starting from B up to C. The whole of that distance is small a. Then I have decided to drop a perpendicular height. That perpendicular height will be taken from A to meet BC at right angles. We are going to drop a perpendicular height, that red broken line from the top, going to side BC, which is our small a, in such a manner that that line perpends line BC. In other words, they will meet and form an angle of 90 degrees. That being the case, you'll realize that I now sit with two triangles. The first triangle is ABD. So we have triangle ABD, which is right angled. Then we also have triangle ACD. Both triangles are right angled triangles. They are right angled triangles, both of them. So we'll now going to apply Pythagoras' theorem. We are going to say let the height of AD be h. Let's call that height h. Then from there, we are going to apply Pythagoras' theorem to either diagram. We have two diagrams that have formed a 90-degree angle. Actually, there are now three triangles involved. There is the original triangle. By introducing AD, we realize that we have formed two other triangles, which is ABD and ACD. Otherwise, both triangles form ABC, the original triangle. Right. So we want to have a look at how this sine rule is proven. We are going to look at the first triangle, which is ABD. Right. Let's focus on triangle ABD. I'm going to extract it out. ABD. This is my triangle A, B, and then D. We said at AD is H and AB is C. This is our height. This is our C in terms of sides. That's a right angled triangle. We are going to apply Pythagoras' we can apply the sine rule here and say, what is sine of B? We are going back to SOHCAHTOA. SOHCAHTOA. There. Right. We are going to find the sine of B. How do we find the sine of B? Our sine of B is equals to opposite side divided by the hypotenuse side. If we were to apply trig ratios, now that the triangle is a right angle triangle, we may as well apply trig ratios. So our sine of B equals to the opposite side divided by the hypotenuse side. Our opposite side is H, so we're going to have sine of B is equals to H divided by C, which is the hypotenuse side, longest side in that right angle triangle. We have found the sine of B now. I want to make H the subject of the formula. Quickly make H the subject of the formula and call that your equation 1. Let's all make H the subject of the formula. Yes, let's work. And before we can even continue further, every time you are dealing with trigonometry, always check if your calculator is in the right mode. Otherwise, if your calculator is in gradients, all your angles are going to be affected. Always make sure your calculator is in degrees. How do you check if your calculator is giving correct answers? When you press sine of 90 degrees, it must always give you 1. That's how you test before you sit for an exam that involves trigonometry. Tan 45 is 1. So when you press on your calculator and get tan 45 is 1, you know your calculator is in the right mode for angles. Our angles are degrees. Otherwise, you may as well change those to other functions, but it will affect your answers. Always stick to degrees in trigonometry. Right, I guess you have met your h, the subject of the formula. I will form a fraction on my left hand side. Sine b is equals over 1 is equals to h divided by c. Then you cross multiply. Our c sine of b is equals to h. This I will call my equation 1. I will call this equation 1. Then you do the same with the other side of your triangle, which is triangle ADC. In triangle ADC, I will look at this as 90 degrees. I will come to this corner here, which is my angle C. I will so long take advantage of this space and proceed and say, if I were to use triangle ADC, in triangle ADC, right? Let me get rid of this for you. Right. We are saying in triangle ACD or ADC, what do we notice? If we say sine of C is going to be the opposite side divided by the hypotenuse side. We have changed the triangle now. Our opposite side is still h, so it's going to be sine of C is equals to h divided by our hypotenuse this time is going to be b. Again, we're going to make h the subject of the formula. So we're now going to sit with cross multiplying. Our h will give us b sine of C. This is what we are familiar with from lower grades. What we did here, we broke down our triangle into 2 triangles. The first triangle was ABD. The second triangle was ACD. We positioned ourselves at B and we identified our opposite side and our hypotenuse side there. This was otherwise our opposite side when we are positioned at B. So sine of B is going to be the opposite side, which is h over c. And then from the other end, triangle ADC or ACD, our sine of C is equals to the opposite side, is the same side, which is the hypotenuse over the hypotenuse side, which means this time I'm using this hypotenuse on the other side. So we basically have 2 hypotenuses here, one being C when we are using triangle ABD, the other being B when we are using triangle ADC. From either side, we can find sine C and sine B. So our sine C is our sine C is equal to h over B. Therefore, our h becomes B sine C. Then, we are now going to equate the 2. We have this other equation which says B sine C is equals to h. We basically have 2 equations that speak to h. So we are going to equate them and try to see how far we can go. How to equate these 2? Remember, this is h, that is also h. So this implies our C sine of B should be the same as our B sine of C. Then from there, we want to isolate these. We can see we have a C on the left-hand side, we have a sine C on the right-hand side. So we are going to, in this case, introduce a common denominator. That common denominator is going to be my BC. In other words, we have indicated that our H is equals to C sine B from the first diagram, and then our H again is equals to A sine C. We now sit with 2 equations that speak to H. I want you to equate those equations like I've already done it. Then from there, we are going to divide both sides by the product of A and C. There is a reason why we are dividing both sides by the product of A and C. In short, what we are saying here is that we now have our C sine B is equals to B sine C. If I find the product of B and C is going to be BC, I will divide both sides by BC. Once I divide both sides by BC, what do I get? The C divide and go this side, and then the B divide and go on the other side. What is left is going to be my sine B over B is the same as sine C over C. It all stemmed from the diagram that we started off with here, where we said we are going to drop a perpendicular in that acute angle triangle and form a 90-degree angle. But we know some of angles on a straight line at D there, meaning we have D1 here and D2 there. At D1 and D2, those angles are both 90 degrees. They build a straight line. Sum of adjacent angles on a straight line is always 180 degrees. So taking either diagram, you are obviously going to have an equation of or an expression of some kind, meaning ABD is a triangle on its own, ADC is another triangle, in which case we can apply sine of B, we can also apply sine of C. We can't apply sine of A from either side, whether you want to talk about A1 or A2. We can't apply that because there are some missing parts, which is BD is unknown and DC are unknown. So I won't focus on A. I will focus on B, which is a solid angle, and C, another solid angle in a right angle triangle. Therefore, we can apply the trig ratios, which is SOHCAHTOA. We are applying sine, opposite side divided by the hypotenuse side. So having equated these, you'll always realize that you have a function sine of B, but the coefficient is C. You're basically going to eliminate C if you decide to take the longer route. Some learners can choose to say, okay, I don't understand why you are finding the common denominator. The whole idea is to separate these variables. The B's must be on one side and the C's must be on the other side according to the sine rule. So how do I convince the next person? I'm going to redo the question with you using another approach so that you can see how else you could have done the same question without necessarily finding the common denominator. You last said your C, your H is equals to C sine of B equals to B sine of C. This is actually B sine of C. Then from there, I'm going to divide both sides by C. The C's will divide and go. That's what I'm saying. I don't want C with B. So I'm going to divide both sides by C. Then I will sit with sine of B is equals to B sine of C divided by C. Next, I want to get rid of B from the other side, which is your right-hand side. So on our right-hand side, I see there is a coefficient B. I'm going to divide both sides this time by B. I'm doing it one at a time. Then the B's will divide and go. So I was taking one letter at a time this time around. At the end of it all, I'm left with sine of B divided by small b is the same as sine of C divided by small c. So meaning I have already established a relationship in this triangle that when you have a non-right angle triangle, ABC, the sine of B divided by the corresponding side B will be the same as sine of C divided by the corresponding side C, which will obviously entail that the sine of A will be divided by small a. We proved these two by fixing A at the top. It came to B and C being the angles involved. This time around we may change and put B at the top so that A becomes in line with C. The same result will be obtained, but this time around it will involve our A. Okay, right. I'm going to give you a few minutes to reflect on this diagram. This diagram says consider an obtuse angled triangle ABC. Why this time are we considering an obtuse angled triangle? Our triangle is ABC, meaning there is an obtuse angle here. That's our obtuse angle. Our angle A, let me call it C1, and then this one C2. Our angle C1 is an obtuse angle. Some books call this triangle an obtuse angled triangle because it contains an obtuse angle. The biggest angle in that triangle is an obtuse angle. It's an angle that is greater than 90 degrees. Otherwise, if that angle was 90 degrees, then the diagram or triangle would be called a right-angled triangle. So what we must realize is that in an obtuse angle triangle of this nature, we can only have our perpendicular height outside the triangle. That's what you see there in broken lines, red lines. Our height HBD is in broken line and is outside the triangle. Not all triangles, depending on the base that you choose, will have their heights inside the triangle. If I choose AC to be the base, then definitely our height is going to be BD, which is that perpendicular height outside the triangle. Again, I'm realizing something here. I'm realizing that triangle ABD, including the red lines now, is a big right-angled triangle. And our triangle BCD is another right-angled triangle, which is smaller than the first triangle. Now, we want to prove this time around that sine of A over small a is the same as sine of C over small c. This time around, I'm not going to focus on D. I'm focusing on angle A and angle C. But the unfortunate part of this diagram is that our perpendicular height is outside the triangle. Hence, we are saying consider an obtuse angled triangle. I want you to apply the same approach that we applied earlier on. Focus on A. Look at which right-angle triangle you can use to define A in terms of trig ratios. Next, focus on triangle on C2. Check which triangle you can use to define your trig ratios. Trig ratios require a right-angled triangle. So I'm going to give you about 4 minutes. The most, actually 4 minutes is too much. Let me give you 2 minutes to come up with some statements there based on the diagram together with the word SOHCAHTOA. We are specifically focusing on sine is equals to opposite over hypotenuse. And you can't use this ratio if there is no right-angled triangle. Identify a right-angled triangle there. Look at the non-sides in that triangle. I see A, I see C, and I don't see small b today. It's for a reason. I see the height. Play around with those two triangles and come up with some statements that will involve the height, just like before, and then simplify it further and see whether it's going to yield a particular ratio or ratios that are equivalent, equal in value. This time around, I deliberately chose an obtuse angle triangle. Let's have a look at what you have there. What do you have there? You considered a triangle. We want to prove that sine A over A is the same as sine C over C, because those are the two angles that I'm seeing there. I'm going to ignore B for now. Right. So if we want to prove that sine A over A is equals to sine C divided by C, how do you proceed? You look at the first triangle there. Your first triangle that you are going to take, which is a right angle triangle, I'm going to take triangle ABD. In that triangle ABD, we have our height H. Well done to that. Then we have our corresponding side AB, we already saw it was labeled earlier on with the original diagram. That is actually our small c. Then we are going to apply our ratios and say sine of A is equals to opposite side, which is h divided by c, the hypotenuse side. Then we make h the separative formula again. This time it implies that our h is equals to c sine of A. Done. That's your first part. That's your first diagram. Then for the second diagram, now we must be very, very careful. Your second diagram is this small triangle BCD. Your triangle BCD. This is our triangle BCD here. This is our angle C2 there. In that triangle C2, what we notice? These are sum of angles on a straight line, meaning our angle BCD, which is your C2, is the same as 180 degrees minus the angle, which is C1, which is originally our C from the main diagram. Remember, we said these vertices A, B, and C stand for angles. So capital letter A is the angle at A, capital letter B is the angle at B, capital letter C is the angle at C in the original diagram. Otherwise, our C2 is no longer in the original diagram. Our C2 is therefore sum of adjacent angles on a straight line is going to be 180 degrees minus that obtuse angle which is at C, which I have labeled as C1. It's actually C. That's why the corresponding side is small c. Remember again, we did not have point D. We added point D ourselves by dropping a perpendicular line from B to D. Well done to that, if you noticed that. Otherwise, those red broken lines indicate that they are not part of the original diagram. We did some construction there so that we can have a 90-degree angle. Then from there, what we do, we're going to focus on this small triangle BCD. Again, this is our height h, and this is our small a. From there, we apply again our sine ratio. Sine is opposite, so this time is sine of 180 degrees minus c, which is your new angle. That angle is no longer c. It's outside the triangle. Sum of angles on a straight line is actually 180 degrees minus the angle at c. That's why I've written it as 180 degrees minus c is equals to opposite side, which is our h over a. Then don't forget reduction formula. We have done reduction formula, sine of 180 degrees minus theta. In which quadrant is that? Yes, it is in the second quadrant. And how is sine there? Yes, sine is positive. So our sine of c is equals to h over a. In other words, that angle reduces to sine of c. 180 degrees is in the second quadrant, wherein if we reduce that using special angles, it comes to sine c. Then we are going to cross multiply and solve for h. Our h will then become a sine c. It's now taking you back to what we explained earlier on. In triangle ABD, our sine A became h over c, leading us to h is equals to c sine A. Then in triangle CBD, that small triangle, our sine of 180 degrees, which are sum of adjacent angles on a straight line, was equals to h over a. Then from there, sine of c, we have reduced. This is our reduction. We have reduced to sine c equals to h over a. Then you make h the subject of the formula. We equate the two. Again, after equating the two, it's up to you to decide. You are going to say c sine of a is equals to a sine of c from the two triangles. You can divide both sides by c, both sides by c. This side c will divide and go. We are left with sine of a is equals to a sine of c divided by c. I want to get rid of a, so I'm going to divide both sides by a. Divide this side by a, divide that side by a. the a's will divide and go this side. Therefore, this will lead you to our sine A over A, which, oh sorry, it's this one. Our sine A over A is equals to sine C over C. But remember, earlier on, we said sine C over C is the same as sine B over B. So it means these three are equal. Why then did we pick a different diagram altogether from the first one? We're trying to indicate to you that it doesn't matter what type of a triangle you work with. Whether you work with an acute angle triangle or you work with an obtuse angle triangle, the result will always be the same. The result will always be the same. At the end of the day, we are establishing that in any right angle triangle, this is our conclusion. The sine of A divided by A, side A, is the same as the sine of angle B divided by the corresponding side B, which is the same as sine of angle C divided by the corresponding side C. Then this same ratio or these same ratios can be written by starting with the sides. Side A divided by sine of angle A is the same as side B divided by the sine of B, angle B. Then side C is the same as C divided by sine of C. This was actually an error. It should be C of sine of C. Right. So this is what we mean by the sine rule. The question is, when do we use this sine rule? The sine rule is used when the following conditions apply in a non-right angle triangle. When you are given two sides and an angle opposite one of the two sides, you can apply that sine rule to find a missing side. When two angles and a side opposite one of the two angles are given, you can also apply the sine rule to find whatever is missing in that triangle. So whenever you are given two sides and a side opposite one of, an angle opposite one of the sides, meaning this is the side given and there is the angle opposite that side. When you have such a situation, you can as well find this missing angle here because you know the corresponding side. You are going to form a ratio and simplify. Alternatively, when you are given two angles, which is this angle at the bottom and that angle at the bottom, and a side opposite one of those angles, you can as well apply the sine rule to find that third missing side, which is directly across the star angle, because the star angle goes with the marked angle, marked side that has a question mark there. So when you have such a situation in maths, you are given two angles in a triangle and a side opposite one of those angles, you can apply the sine rule to get the missing side that goes with the other angle. Or when you are given two sides and an angle opposite one of those sides, you can find the missing angle. So it's either you are looking for an angle or you are looking for a side. Okay, right. Use the triangle below to verify the sine rule correct to two decimal places. This is exactly what we are emphasizing now. To say, suppose this is your triangle. We want to prove beyond reasonable doubt that sine of angle A divided by 7.07, the corresponding side, is the same as the sine of 70 degrees divided by 8.69, and will be the same as sine of 60 degrees divided by 8. You pick an angle, look across, look at the side that goes with that angle. Pick an angle, look at the side that goes with that angle. Find the sine of that angle, divide by the corresponding side, or vice versa. Start with the side, divide by the sine of that angle. You will find that all those three ratios are going to be the same. All those final answers are going to be the same. This triangle has been constructed for you. It means all the measurements have been done to scale. It means all the angles were actually measured, and it's exactly 50, 70, 60 degrees for it to have the dimensions that it possesses. So I want you to quickly confirm that sine of A divided by small a is the same as sine of B in any triangle divided by B, which is the same as sine of C divided by side C. That's what I want you to confirm. I'm just going to give you less than a minute to confirm that. Work out each fraction on its own and see if the results are going to be the same. That's basically what the sine rule says. That's basically what the sine rule stipulates. Sine of an angle divided by the corresponding side will always be the same as the sine of another angle divided by its corresponding side, same as the sine of the third angle divided by its corresponding side. Those answers should always be the same, or those ratios should always be the same. Let's quickly confirm that. Right, what I'm basically saying here is I wanted you to say sine of 50 degrees divide by 7.07, the corresponding side. This you punch on your calculator. I said give your answers correct to 2 decimal places. If I press sine of 50 degrees divide by 7.07 and then get the answer, I'm getting 0.11, correct to 2 decimal places. I proceed. Next, I find sine of 70 degrees. I'm now at B. Divide by the corresponding side. What is our small b? Our small b is the side that is across angle B, which is 8.69. Correct to 2 decimal places, that side. Then if I press on my calculator, sine of 70 degrees divide by 8.69 equals, I get 0.108134939. Correct to 2 decimal places, I'm getting 0.11. Then I go to the last one, sine C. My sine C is sine of 60 degrees divide by 8. I press on my calculator, sine of 60 degrees divide by the corresponding side, which is 8 units. Divide by 8, it's giving me root 3 over 12. I press SD to convert to a decimal. Again, I'm getting 0.11. I'm getting 0.11. So what I'm realizing is that in any triangle, if that triangle has correctly been drawn to accuracy, the sine of an angle divided by its corresponding side of all the 3 angles, the ratios will always be the same. The fractions will always be the same. As a fraction here, I can say 11 over 100. This is also 11 over 100. This is also 11 over 100. All of them are giving me 11 over 100. Sine A over small a, sine B divided by small b, and so on up to sine C divided by small c. They all yield the same result. And this is how we exactly prove the sine rule. You start with a diagram. In consolidation, you start with a diagram. You drop your perpendicular height. After dropping that perpendicular height, you will always have in an acute angle triangle 2 right angle triangles. Apply the sine trig ratio to say sine is opposite side over hypotenuse side to either diagram. Then you will find that every time you do this, it will involve h. Both equations will involve h. Then you are going to equate your 2 expressions for h, then divide both sides by the letter that you want to get rid of, so that you separate those variables so that they can both read the same. If it's b going with small b and c going with small c. You can take it step by step or create a common denominator for the letters, which in this case is bc, but never mind. You can still say divide by c both sides, get rid of c, divide by b both sides, get rid of b. You will find that these will naturally separate. Then I deliberately chose an obtuse angle triangle, and in this case my other triangle was formed. Actually, both triangles extended into the outside, but the main focus is triangle ABC. So the reason why we chose this obtuse angle triangle, we wanted to show each other that it doesn't matter what type of a triangle you work it with, the sine rule will still stand. You just have to apply your basics. SOHCAHTOA, sine is opposite side divided by the hypotenuse side. But don't forget, if you use this obtuse angle triangle, your C2, the new angle at C, which is outside the triangle, is no longer going to be C. It's now going to be 180 degrees minus C because of sum of adjacent angles on a straight line. Then from there, you use reduction formula until you have proven. Right. So we have confirmed that according to this diagram that was drawn to scale, it works. Right. Here is our first example. It says determine the value of x in the following triangles. Give your answers correct to 2 decimal places. Note the diagrams are not drawn to scale. These are just but diagrams. They are not drawn to scale. Never measure from them. Don't take a ruler and start measuring to find how long is BC. We want you to apply a skill that you learn to find the area of this, the side that is missing there. In this case, they want you to determine the value of x, which is side BC, opposite big A. We are going to take one triangle at a time. Our first triangle is ABC. It contains 2 angles and a side opposite one of them. The side is 25 meters across 65 degrees. So in short, I'm going to label my sides based on the letters that are used. I see the top letter is C, so this is small c. I see the first letter on my left is A, so this is small a, which is actually x. Then the other letter is a B, so it's across small b. So we know our small b, we know our angle A, we know our angle B. We need to find small a. We can as well also be asked to find both big C and small c using some knowledge or theorems there, especially for angle C. Those are some of the interior angles of a triangle. Right, having done that, I want you to quickly write down the formula that you can use to find that missing side BC. This is where you apply the sine rule. You look at what is given, then apply the sine rule. In this case, I want to look for small a. I know big A, which is the angle. I know small b. I know big B. So my formula, I'm going to take only 2 of those, which is A divided by sine A is equals to B divided by sine B. And I'm going to give you a tip on these ones. When you are looking for a side, always make sure the sides go to the top. It makes it a bit faster. When you are looking for an angle, make sure the sine of A goes to the top. Remember, those are equivalent. They are equal in value. Whether I take them or find their reciprocal, turn them upside down, the answer won't be affected. Right. Right. Having done that, we are going to substitute. You know your A is x. So I'm going to replace, in place of x, A, I put x. Then I know my angle A is 70 degrees. That's my A. The angle is 70 degrees here. Right? I substitute. Then I go to B on the other side. I have 25 for B over sine of 65, which is angle B. Now, you can already see there is only one thing missing there. It's x. Go ahead and solve for x. Yes, you can think of cross multiplication there. It's going to work. But the whole idea is to make x the subject of the formula. Whichever approach you use, make x the subject of the formula. So, in this case, I'm going to multiply both sides by sine of 70 degrees, even this side by sine of 70 degrees, like that. We'll multiply both sides by sine of 70 so that these divide and go. Then you'll get your x is free now. So our x is going to be 25 multiplied by sine of 70 degrees, divide by sine of 65 degrees. The rest is calculator work. You press your fraction symbol on your calculator and press 25 sine 70 degrees divided by sine 65 degrees. You'll know the value of of side BC, which is x. If you are not going to get the answer that I'm going to display right now, then something did not go well there. Your x should give you 25.92 meters. So it means that side x or small a or BC is exactly 25.92 meters, correct to 2 decimal places. If you got any other answer besides this one, check your calculator. Maybe your calculator is not in degrees, and hence that will affect, or hence your answers were affected. So how did we proceed in this question? We said first things first, you have to check what is given. I see angle A is given, angle B is given, so I have to have sine A and sine B. But both sine A and sine B must go with their corresponding sides. So I'm going to form some fractions, replace what I know. I know A is x, I know angle A is 70, I know B is 25, I know angle B is 65. Then I'll replace and form a fractional equation which I'll then solve for x. Again, if you punch on your calculator sine 70 degrees divided by 25.92, you'll get the same answer as taking sine of 65 degrees divided by 25. The end result will be the same. This is basically how you can use the sine rule to find a missing side in a non-right angle triangle. Not all triangles can be solved by using Pythagoras' theorem. Okay, then we move on to the next question. In the next question, we are given angle P, and we are given small p. This is our small p. We are given angle Q, and then there is our small q. We are given letter R, capital R. This is our small letter r, which is x that we need to find. So we have a problem in this question. The letter that we need to find, that is side PQ, there is no corresponding angle. And the sine rule won't apply if that's the case. Because the sine rule, you need to have 3 items. It's either you have 2 angles and the third side, and unfortunately here the side that they want me to find has nothing to do with those sides Q, so I can't apply Q. Yes, if I was looking for Q, those are 2 angles and a side opposite one of them. But this time I'm looking at R and X. Both are not known. But going back to our knowledge of triangles, our angle R can be found using the sum of the interior angles of a triangle is always 180 degrees. That's the sum of the interior angles of a triangle. We are going to add 28 degrees to 54 degrees and then subtract from 180 degrees and obtain 98 degrees. So it means our angle R here has been found as 98 degrees. The whole of that angle R is 98. That being the case, now we can confidently proceed to find the corresponding side small r. And this time around I'm deliberately used the P, Q and R so that you drift away from this mindset to say the formula is always in terms of A, B and C. It depends on the letters that have been used. So on that note, we are going to customize our formula, change it to meet the diagram. Small p must go with side big P, and then angle big P. Small q must go with side angle big Q, and so on. So my formula is therefore going to be R divided by side R is the same as P divided by side P. Because I don't have A, B and C today, I focus on corresponding sides going together with their angles. So our angle P goes with small p. Small p being the side that is directly in front of capital letter P. Then there is our formula. We then substitute. Where there is PR, we put X. Then our R is 98 degrees. Then equals to 12 divided by sine of 54 degrees. again we multiply both sides by sine 98 degrees. You can cross multiply, but cross multiplying will take longer because you are going to say x sine 54. Then later on you divide again by sine 54. So the easiest here is just multiply both sides by sine of 98 degrees. Multiply this side by sine 98 degrees because this is like an equation. What you do on one side should surely be done on the other side, so that these can divide and go. Then you are left with your x equals to 12 sine 98 degrees divided by sine 54 degrees. Yes, then from there you punch to get the final answer on your calculator. How big is that side x? Our side x this time is going to be 14.69 centimeters. So this was a question where what we were asked to find, when you look across you don't see any angle, then you get confused. You must think the sum of the interior angles of a triangle is always 180 degrees. Add those two and separate from 180. You'll know the angle that will help you get side x, which is your small r. Once I get that 98 degrees, then everything will flow because I already have a complete pair, 28 degrees versus 12 centimeters. They go together. I just needed one angle, either an angle or a side, but since I'm asked to find a side, I needed that angle r. Hence, I found that angle r using sum of interior angles of a triangle. Then this time around, we are going to determine the size of the angle alpha in the following triangle. Give your answers correct to 2 decimal places again. We'll always emphasize these diagrams are not necessarily drawn to scale, so never measure from them. And this time, what is missing is our angle V, which has been labeled as our alpha. So we want to find the size of that angle. This time around, we can't apply the sum of the interior angles of a triangle because there is only one angle that is known, angle T, 66 degrees. So again, we are given two sides and an angle opposite one of them. We can as well apply our sine rule. Let's proceed and have a look at how we apply it. This is where I emphasized earlier on to say, if you are looking for an angle, rather have your sine of an angle as your numerator, then the sides become your denominators. It makes it faster in calculation. Otherwise, you can still maintain your letters at the top for any diagram, but it usually becomes faster depending on what you are looking for. If you are looking for a side, make sure the sides are at the top. If you are looking for an angle, make sure the angles are at the top. Either way, it works equally the same. That's just but my choice. So sine V divided by V is the same as sine T divided by T. Why am I speaking to V? Because that's the angle that we have been asked to find. Yes, we have sine alpha over 11.5, they go together, is the same as sine 66 degrees divided by 10.8. Then from there, we multiply both sides by 11.5 so that we make our sine alpha the subject of the formula. This should be actually equals to that. Then next, we now want to solve for alpha. This is where we are going to say shift sine, which gives us arc sine of 11.5 times sine 66 degrees divided by 10.8. Remember, in trigonometry, you have already done equations. You know how to solve for an angle. So in this case, our value is 11.5 times sine 66 degrees over 10.8. You don't have to convert that to a decimal. Otherwise, that is called early rounding off, and it comes with the early rounding off problem, the margin of early rounding off, error. We call it a marginal error, early rounding off error. So never convert those to decimals until you get to the final answer. Only round off the final answer. Don't press 11.5 times sine 66 degrees divided by 10.8 and then you round off to 2 decimal places. It's going to affect your final answer. Rather, keep it as a fraction, introduce brackets, and evaluate that. This will give us arc sine of that is 76.60 degrees. So it means that angle at alpha is 76.60 degrees. That's how you determine the angle if it's hidden from you. Otherwise, we use the same formula to find the sides. It depends on what is given, but the formula will remain the same. You have to craft it or coin it or customize it based on the diagram. Capital letter V goes with small v there. Capital letter T goes with small t there. Capital letter U goes with small u there. But my focus is not on U because the angle I'm looking for is alpha, which is at V. Hence, my formula will be sine V divided by small v is equal to sine of angle T divided by small t. Then you replace for what you know and simplify. Otherwise, that's how you apply that sine rule as an example. Let's move on to the cosine rule. So in the cosine rule, we're saying in any triangle where all three sides are given or where two sides and an angle between the sides is given, then the following apply. A squared is equals to b squared plus c squared minus 2bc cos of angle A. Or if you are looking for b squared or side B, you say b squared equals to a squared plus c squared minus 2ac cos of B. So you'll realize something here. If you are looking for side A, the angle must be A. If you are looking for side B, it means you have to know side angle B. If you are looking for side C, it needs the other two sides, then the angle C must also be known. So we're basically saying you have to have two sides and an angle trapped between those two sides. If I'm looking for small a, you can check which sides are affected. Is side I'm looking for small a here. I need to have this angle here at A, and I need to have those two sides. That's what we mean by two sides and an angle between them. That formula will then apply, or that rule will then apply. So this is a rule that speaks to cosine. That's what we mean by the cosine rule. So we're going to have a look at how we prove the cosine rule. The approach is almost the same in terms of the sketch, but it will differ alongside or along the way. What we are saying here is that we are going to drop a perpendicular height. The side that is opposite our angle A is small a. If we let our side DC to be x, let our side DC be x. But remember, the whole of BC is our small a. If you cut out DC and make your DC x, therefore, what remains is your BD. We are cutting out x from A, so our BD is going to be A minus x. Meaning, if BC was 10 centimeters, then DC, we make it 4 centimeters. Then what remains as our BD is going to be 10, the whole length, minus 4, which will then give us our 6. So this time around, we are going to focus on all three at the same time. All three sides are involved. A also has to play a part. We are going to calculate all the missing sides in terms of variables. If we let DC be x, therefore our BD will be that length A minus x. It means the whole total length was A, but you are losing x, which is cutting out DC from BC. We'll be left with A minus x. That will then become the length of your BC. You can even confirm that is correct, because for you to get to BC, BC equals to BD added to D to C. You have arrived from B to C. You moved from B to D, then you connected from D to C. But I've already broken it down into parts. Our B to D is going to be A minus x, that's B to D, add our DC, which is x. Then when we simplify algebraical like terms, x minus x is 0, you'll find that BC goes back to A. So I did not affect the diagram in any way. I just broke down the length BC. By so doing, I sit with right angle triangles, two of them, right? Then from there, we are going to apply our Pythagoras' theorem. Since all three sides are known, I will apply Pythagoras' theorem. So the first diagram, we are saying in triangle A, B, D. What do we notice? We realize that this is our hypotenuse side. So we are going to say the longest side is our C. So we are going to say C squared equals to, according to Pythagoras theorem, equals to A minus X squared, then plus the other side, which is H squared. Then from there, we are going to simplify. Our C squared equals to, we expand this, is going to be A minus X multiplied by A minus X, then plus your H squared. Then you simplify further. This will give you C squared equals to A squared minus 2AX, if you group like terms there, and then plus X squared. You can expand that, you'll get this. Then plus your H squared. So it means our longest side squared is equal to the sum of the squares of the other two sides. That is Pythagoras' what? Theorem. I'm going to do it on only one side, then I want you to do the other side. Apply Pythagoras theorem in triangle ADC. I've done this one with you in triangle ABD. Applying Pythagoras theorem there, we are going to, this is our Pythagoras theorem, Pythagoras there, right? Theorem. I've applied it there. I want you to apply Pythagoras theorem in the next diagram. ABADC. Apply Pythagoras theorem also. I want you to apply Pythagoras theorem there. In triangle ADC, what do we notice? Yes, B squared is the longest side in that triangle, equals to H squared plus X squared. Oh, wow, look at this. Look at this. Look at this. We can replace that. That is X squared plus H squared is the same as B squared. That's what I'm noticing here. It is equals to B squared. So meaning I can as well replace in my equation 1, I can replace those two, H squared plus X squared is B squared from the second diagram. So it means our C squared is equals to A squared plus B squared, replacing that, minus twice AX. Done. That's the expression. But unfortunately, I have an X in that expression. So what we have done so far here, we have two triangles that are complete in terms of their sides, including our X. Then we are applying Pythagoras theorem to either diagram. Then along the way, we realize that from the second diagram, our B squared is equal to X squared plus H squared, which is contained in the other diagram as an expression. So we're going to replace X squared plus H squared and put B squared. So far we have C squared equals to A squared plus B squared, then minus 2AX. Then there is a problem there. We now have C squared equals to A squared plus B squared minus 2AX. We have to get rid of this X so that we have no X. Remember, it's us who introduced that X. Let's get rid of that AX. How do we get rid of AX? We focus on triangle ABD. In triangle ABD, what we notice, if we say cosine, let me erase this. If we say cosine of C, we position ourselves at angle C here. Cosine of C is adjacent side divided by the hypotenuse side. So our cos of C is going to be the adjacent side, X over B. I want to solve for X so that I can go back and replace that X there. If I make X the subject of formula here, I'm going to cross multiply. My X becomes B cos of angle C. That's how I found X there. In the smaller triangle ADC, where I see X, B, and H. I chose to position myself at point C. then when I'm at point C, x becomes the adjacent side because I have a problem of x in that expression above. So I have to form an expression in terms of x and solve for x. And it gives me b cos c. We then replace and say, therefore, our c squared is going to be a squared plus b squared minus twice a times. Replace x and put b cos of c. Therefore, the final step is c squared equals to a squared plus b squared minus twice ab cos of c, which is one of those rules that we saw earlier on, that when you are looking for small c, you need small a, you need small b, and angle c. This is how you prove the cosine rule for any of the missing side. So here, if I put BC as a base, then we are looking for small c. Right, let's proceed and have a look at how you could have done that. This time around, okay, this is where we have ended. We eventually found our cos of c is x over b. Then we solved for our x and replaced our x here. This was originally our x there. All right. Then we move on to choosing another side. This time around, I want an obtuse angle triangle. So what does this mean? This time it means I have an angle outside. It's still a right angle triangle, two of them. Again, we'll see how we play around with them. Again, our angle B2 here is going to be sum of angles on a straight line. Remember that big capital letter B is for the original triangle ABC. Right. So if I extend B to D, let's call that length X. Otherwise, all other sides are known is A, B, and C. But today, our AD is not going to be short. It's going to be elongated by X units. It's A, B, D. From A to B is C. From B to D is X. Therefore, the whole length to form a right angle triangle is going to be AC plus X, which is A to B is C, B to D, we have said let it be X. So the whole length is now going to be C plus X. Again, we are going to apply our Pythagoras' theorem, bearing in mind that if we are looking at triangle, let's look at triangle ADC. In triangle ADC, what are we saying? We are saying B squared is equals to C plus X squared. In the actual fact, we are saying AC squared equals to AD squared plus DC squared plus DC squared. That is your Pythagoras' theorem. Right. Now, replacing our A to C is B, so we're going to have B squared. Our A to D is C plus X. Then we square. Then our height is our DC, which is H. Then we expand and simplify. We are getting C squared is equals to, actually B squared here is equal to C squared plus 2CX plus X squared. Then plus that H squared after expanding. Then we go to our second triangle, which is BCD, this one here, which is the outside triangle that we have extended and produced. BDC is our new triangle, small one. But this triangle is using 180 degrees minus B, sum of angles on a straight line. Right. At the same time, it's a complete triangle. Its hypotenuse is A. The adjacent side to B is X, otherwise the opposite side to B is H. We apply Pythagoras' theorem again, we get A squared equals X squared plus H squared. Again, we realize that this can be replaced using A. So it means our B squared is going to be A squared plus C squared plus 2AX. This time around, it comes with a plus. There is no minus because we extended, moved forward to the outside of the triangle, because our perpendicular height was formed outside, not within the triangle. That's an obtuse angle triangle. Right. Having said that, what are we saying? We'll realize that in triangle CBD, our angle CBD is 180 minus B. Big B is the angle in the original. So subtracting that angle from a straight line will give us angle, what I will call here B2. That's your B2 there. Right. In that triangle, we want to solve for x. Remember, we have to get rid of x in this equation. We have to get rid of this x here. So we do likewise in the previous approach. Cos of 180 degrees minus b is equals to x over a. Using that small triangle, it's minus x over, it's x over a. Then let's reduce. Remember, we are in the second quadrant where cosine is negative. So what does this mean? It means our x, when we cross multiply, is going to be a cos 180 degrees minus b. But we know in the second quadrant cosine is negative. So it's going to be negative a cos b. Then where we see x here, we are going to replace and put a negative cos b, or negative a times cos b, because we are saying cos of 180 degrees minus b is the same as negative cos of b, because we are in the second quadrant. Yes, that's reduction formula. This will then be multiplied by our a. Therefore, our x will become negative a times cos of b. Multiplying those two, then we are going to replace our x and get this equation. So it means if it's b squared, we need a squared plus c squared minus twice the product of a and c cos of b. The same applies to c. If we're to work it out with a, you can continue with the same diagram, swap around, put bc at the bottom, then have a at the top. You'll be able to get the a squared also. Alternatively, you can swap around and put your a here and then your b there, then your c up there. This will be small a. Then the same result will be obtained, wherein you are going to get a squared equals to b squared plus c squared minus 2bc or plus 2bc. Right, so times cos of a, if there is an a. So we have proven this theorem, or rather this rule, using the a squared, b squared, and c squared. So in our case, we focused on c squared. We focused also on b squared. You can as well do it for a squared using a similar diagram. Relabel your diagram. Where you have a here, you can put a b there and your a there, and your c can be maintained. This will then be your small a. Apply the same approach, it will eventually lead you to the same result of a squared equals to b squared plus c squared minus twice ac cos of angle a. Then the question is, when do we use the cosine rule? We use the cosine rule when all three sides are given, or when two sides and an angle between them is given. This is where the sine rule fails us. We can't use the sine rule in this question because all angles are missing in the first diagram. In the second diagram, the corresponding side to the given angle is unknown. This is where we'll apply the cosine rule. So the cosine rule is used when three sides are given, or when two sides and an angle between them is given. So in short, a squared is b squared plus c squared minus twice bc cos of big A. So if you start with a small a, you end with a big A in cosine. You start with a small b, you end with a big B, which is your angle. Then small letter c, capital letter C. In between is the other two sides. So if we have C, we'll use A, B sides, and the angle C must be known. It means it's the angle between those two sides. Alternatively, this same formula can be written in terms of cosine by making cosine the subject of the formula in each one of them. So for instance, if you look at the first one, it says a squared equals to b squared plus c squared minus 2a minus 2bc cos of a. If you want to make cos a the subject of the formula, what do? You transpose, you bring a negative 2bc to the left hand side. It's going to be 2bc cos of a is the same as b squared plus c squared minus a squared coming from the other side. Divide both sides by 2bc, this side by 2bc. Then that's how you make cos a the separate formula. You do likewise for the other two. You must go and practice that at home. Right. Then here is where we apply the cosine rule. It says determine the value of x in each of the following diagrams. It depends on what x is missing. Sometimes it's the side, sometimes it's the angle. When I look at the first diagram, what is missing is a side. And I can see I have two sides and an included angle. I want to find an opposite side BC. This is where I'm going to apply my cosine rule. The cosine rule will then say I'm looking for small a. This is small a. I know small b. I know small c. Otherwise, my capital letter A is 48 degrees. Then our small letter a is x. And then our small letter b is 7. Our small letter c is 9. We then replace in the formula a squared equals to b squared plus c squared minus twice the product of those two cos of angle A. We replace x squared equals to 7 squared plus 9 squared minus twice the product of 7 and 9 cos of 48 degrees. Then we proceed and get to the stage where we now have 49 plus 81 giving us 130 minus 126 cos 48. Must be very careful here. Don't subtract these two, because the other one is a product of cos 48. That is not an ordinary 126. It's 126 multiplied by cos of 48. So you can't subtract 126 from 130 and get a 4 there. That remains as is. Then from there, we are going to say x equals to square root of 126 cos of 48 degrees. Square root of 130 minus 126 cos of 48. Never punch these things out before you get to the final. You are solving for x. It's a quadratic equation of some kind. Take square root on both sides and solve for x. You'll obtain your x as 6.76 millimeters. So that's the length of our side BC using the cosine rule. We're using it when two sides are given and an included angle. Then on the other diagram, we are trying to solve for an angle C. Our angle C is x. We are given all three sides. So for us to find those three sides, we have to identify. We want to find capital C. We know small c. We know small a. We know small b. Then we choose a formula. Right. There is our formula. It's going to be c squared equals to a squared plus b squared. The moment we say we are looking for c, then we have to start with small c. The moment we say we are looking for small c, we again have to start with small c. When we are looking for angle c, we also start with small c. Then we substitute. We have identified our c is 36 squared. Our b is 29. A is 29. Our b is 25. Then we substitute as it were until we replace our angle c, which is angle x. We replace that letter c with x. That's the size of that angle. It's unknown. Then from there, we manipulate our equation until we get to a point where we have 1450 cos x is equal to 170 degrees. What we have just done here is to change positions. Then from there, we make cos x the subject of the formula, meaning we need to divide both sides by 1450 and then simplify. that fraction can simplify to 17 over 145. Remember, whenever you're looking for an angle, you say arc cosine, arc sine, arc tan. So I'm solving for an angle here. It's going to be arc cosine of 17 over 145. When you divide both the numerator and the denominator by 10, you'll get 17 over 145. If you want to, you can keep it as 170 over 1450. It will still work. Then when you press that on your calculator, just press that and see what you get. Yes, you get exactly 83.27 correct to 2 decimal places. That's how you can apply the cosine rule to find a missing angle in a diagram. This cosine rule is applicable where you can't apply the sine rule. Right, I'm moving on to the last part of the presentation, that is finding the area of a triangle which is non-right-angled. Our triangle is ABC, is non-right-angled. We drop a perpendicular height, then we'll have our AD being the new height, which is H. Then we have our same size that we have been having before. All these three stem from the same diagram, but you need to know how to angle them. You now know the height of your triangle, and your base this time is your BC. So the area of your triangle is half base times height. It's going to be half base times height. Our base is BC, our height is H. Then we know our BC is A, so it's going to be half of A times H. We're replacing BC and putting our H there. Because we know the height, that red line, broken line. We know the base, depending on which side we choose. If I choose BC to be the base is A, that is BC, the height is H, done. But remember, we are the one who introduced H. We can as well find that H. Our H can be found by saying in triangle ABC, our sine B is equals to the opposite side divided by the hypotenuse side. Then we can solve for H. Our H will become C sine of B. The same applies to the other side. Triangle ADC, we can solve for H again from the other side. We say sine of C is equals to opposite over hypotenuse. My hypotenuse is B. Therefore, my H can also be written as B sine of C, like we did earlier on. But this time I'm finding the area, half base times height. I know the base is A, the height is H, but that H can be written in two different ways. So meaning our area is going to be half A times H, where H is C sine B or H is B sine C. Replacing those two in place of H will lead to area of triangle ABC can be written as half of A times C times sine of B. What does that mean? It means your triangle is like this. This is your angle B. This is your angle A. This is your angle C. This is your small c. This is your small a. So if angle B is given, you need side C and side A. That's what it means. Same rule as the cosine rule. You need two sides and an angle between. Then the sine rule, the area rule will apply. Half AC times sine B. Then half AB times sine C. Then what would happen if you use the half? You want A, so it's going to be A equals to half BC times sine of A. So when the sides are B and C, the angle is A. When the sides are A and C, the angle is B. When the sides involved are A and B, the angle is C, like I've demonstrated on that diagram. So this is what we mean by the area rule. This is where the formula half base times height came from. When the angle is 90 degrees, we know sine 90 is 1. So this formula works for any triangle in this world. It doesn't only work for non right angle triangles. It can also be used even in a non-right angle triangle, because the whole idea is to replace the angle. But it was discovered that when the angle is 90 degrees, sine 90 is 1. Hence, we don't have to say half BC sine 90 degrees. Sine 90 will always be 1. Hence, we say base times height. That sine 90 disappears. Okay. So the same would apply if you changed the approach. So we are saying the area rule is used in a non-right angle triangle where two sides and an included angle are given, and you want to find the area of the triangle. You can find the area of the triangle without a 90-degree angle by applying what we call the area rule, which states what we have just established: half BC times sine A, or half AC times sine B, or half BC times sine A, depending on which angle is given. If I look at this diagram as an example, to find the area, there is no height you can see, perpendicular height, we only see lateral heights, 40 centimeters and 44. Otherwise, the given angle is 36 degrees. How would you proceed to find the area of that triangle? So the first thing first, you have to write down your formula. I thought you said area of triangle A, B, C. You stop there and check which sides are given. It's B and C. So it's going to be half BC times sine. Once you say BC, there is no A involved. It means the angle must be A. Once two sides are given, look at those two sides that are given, BC, the angle must be A, which is the angle between those two sides. Then from there, you substitute. It's going to be half of 40 multiplied by 44, as simple as all that, multiplied by sine 36 degrees, you basically replacing. Then you punch on your calculator, press those things on your calculator, evaluate that directly as it is on your calculator. The answer becomes 517.25 centimeters squared. I don't need the base with this area rule. All I need are two sides and an angle between those two sides. I will identify which sides are involved, then I come up with my formula depending on the diagram. Okay, that's how you apply the area rule. So our focus for this lesson was to have a look at how we prove the sine rule, how we prove the cosine rule, and how we prove the area rule. These three shall be needed when we engage on diagrams that will involve triangles, finding missing sides, finding missing angles, as well as the area of those shapes. Otherwise, the whole idea left for you now is to go and practice and practice. In our next session, we'll have a look at how we apply these rules to answer typical examination types of questions. Otherwise, my focus for today was to take you through how you prove the sine rule, how you prove the cosine rule, to say how do we prove the sine rule, how do we prove the cosine rule, how do we prove the area rule, how do we apply them to find missing sides or missing angles or the area itself. Then the sine rule states that in any triangle, sine of A divided by small a is the same as sine of B divided by small c, which is equal to sine C divided by small c. Otherwise, the sine rule is used when the following conditions apply. In a right angle triangle, that is when two sides are given and an angle opposite one of them, or two angles are given and a side opposite one of them. Okay, what we are saying with the area rule is the following. I'm going to have a sketch here, right? I will call this point like initial. Let me see my original diagram. It was A, B, C. Let's go back to this one. What I said is you start with a diagram like this. When you are proving it, you drop a perpendicular height there because there was no perpendicular height. You are the one who is introducing it. Call it H. This is your A, this is your B, and this is your C. Right? Then from there, you know the whole of this length here going down is your C. This is your C, right? And then this is your small b. And then this is your small a. You already have your height, perpendicular height. That being the case, it means AB is the base. So our AB is the base now. AB is your base of the triangle. Then you go back to primary. How do you find the area of a triangle? Area is equals to half base times height. Done. But I know the base is going to be half. C is the length. I know the height is h. That's my answer. Half CH is the answer. But there is a problem here. You are the one who introduced the h in the diagram. There wasn't an h. So you can now replace h by using one of the two right angle triangles, ADC. Let's call this D. ADC or BDC. Either diagram will work depending on what is given. So if I replace h, I will go back and say but what? Sine of A, right, is equals to the opposite side divided by the hypotenuse side, which is that hypotenuse side. If I'm at A, h is the opposite side. Then you make h the subject of the formula. You will have h equals to b times sine of A. Because I want to replace h, you can do the same from the other side of B. But I'm only showing you how you can do it from side A. Another learner can choose side B. When you are done with this, you replace area equals to half, base is C, height is h, but that h is B, sine of A. Oh, it means I need side B and C. You need side B and C and this angle here and this angle there. So when you have B and C, the angle becomes A. When you have A and C, the angle becomes C. You can still do the same from B side. Apply sine B, you'll get opposite over hypotenuse. This time it will involve A. You'll find that when you have A and C, the angle will be B. When you have B and C, the angle will be A. Then you replace. The whole essence here is to say, how do we find the area of a triangle? It's half base times height. But this triangle did not have a height. You introduced that h yourself. Go back and apply your trig ratios from either A or B and then find h. Then go back and replace h. Otherwise, your base is AB in this case. If your base changes, do likewise again. Drop your perpendicular height, but if your answer comes with that h, eliminate h along the way. Then you find that every time you eliminate h, it will involve sine. Sine A or sine B or sine C, depending on which one you chose to be your base. Whether it's an acute angle triangle or an obtuse angle triangle, it will always work. That's how you can prove the area rule. Okay. Right, so like I said, you will need the sine rule when you have two sides and an angle opposite one of them, or two angles and a side opposite one of them. Otherwise, the cosine rule, you need all three sides. You can apply it when you have all three sides, or you have two sides and an angle between them. That angle between them will obviously lead us to the area rule also. The area rule also needs two sides and an angle between them. Same applies to the cosine rule. So when all three sides are missing in a given, given in a given triangle, you can apply the cosine rule. Or when two sides and an included angle are given, you can apply the cosine rule. Otherwise, the area rule also needs one of those conditions in cosine, which is two sides B, two sides and an angle between. Right, there is your worksheet. Go through these questions. You are asked to find the area of each one of them. They are very tricky because for you to find the area, some of them will have to find some missing sides. This is where you have to think the sine rule, the cosine rule, solve your triangle, find all the missing sides, and then you will be able to find your areas. The focus is on area, but you'll be forced to apply sine and cosine along the way. So basically this exercise requires your knowledge of the sine rule, the cosine rule, when do I use the cosine rule, when do I use the sine rule, otherwise when do I use the area rule. You need to go back, practice them, answer these questions, and consolidate your concepts. Thank you for attending. We'll meet again at some point in time and look at other concepts thereof. Otherwise, thank you and goodbye.